Namaste, hello everyone, welcome to this session. So, in this session we are going to solve some examples on the topics we covered or studied in lectures 11 to 13 of this course on experimental model analysis. As I said earlier, the objective is essentially to further strengthen our understanding of the concepts and topics we studied in these lectures. So, in these lectures 11 to 13 we studied impulse response functions and transient response analysis, FRF or the frequency response function characteristics of single degree of freedom systems, and FRF characteristics of multi degree of freedom systems. Please watch these lectures to know the background theory of the examples we are going to solve in this session. So, let us get started and let us start with example 1. Let me go to next page. Let me write down the problem first. Example 1. Question. So, a force of 25 newtons acts for a short duration (0.6 seconds) on a structure modeled as a single degree of freedom system with parameters given below. Find approximately the amplitude of the resulting displacement response. The parameters are m is equal to 2 kg, k is equal to 4000 Newton per meter, and c is equal to 1.0 Newton second per meter, right. So, essentially we have got this force like this, and it is acting for a short duration let us say this is F naught and this is T naught. So, F naught is given as 25 newtons and T naught is given as 0.6 seconds. Okay. So, essentially we have to therefore find the response of this structure modeled as single degree of freedom system approximately. So, here the force you can see it is not like harmonic force acting with certain frequency, it is a transient force, and the typical force given here is a kind of a rectangular pulse shape force, right. So, let us see how we can approximately find the response of the system. Let us proceed with the solution. So, as we study in the lectures, right, that the response to transient force can be determined in the time domain by convolution integral. So, let us so I think before I know you use the method to find approximately the response, let me first tell you what exactly needs to be done to find the response exactly. So, convolution integral. So, convolution integral says that if the response is say x of t, then and if the force is f of t, then f of tau h t minus tau d tau from 0 to t. So, this is convolution integral, which says that tau here is a dummy time variable. So, we need to integrate the force with the impulse multiplied with the impulse response function, correct, and integrate that over 0 to t, correct. So, we derived in the lectures the basis of arriving at this particular integral, right, that you can see. But then you need to basically perform this integration in order to find the response exactly, correct. And of course, what is h of t here? The impulse h of t is the impulse response function. H of t is the impulse response function, and for a single degree of freedom system, so this I am writing for a single degree of freedom system, for a single degree of freedom system, right. This is given by 1 upon m omega d to the power minus zeta omega n t sin omega dt, correct. And here omega d of course is the damped natural frequency, damped natural frequency, which is equal to omega n under root of 1 minus zeta square, correct. So, therefore, if we wish to apply this method, then we will have to express f, the force, as a function of time. How that can be done? For the present case, the force is can be written as f of t is equal to 0, f0 for t greater than or equal to 0, right, and less than or equal to t naught. So, from 0 to t naught the force is f naught, and then it is 0 for t more than t naught, correct. So, that describes the time domain forcing function. So, using this time domain forcing function and the impulse response function, now we can substitute these two quantities in the integral and integrate and then obtain the equation for time domain response, correct. So, that of course is a little involved process because you have to perform the integration. So, now we are going to use an approximate method to find that response. Let us look at the approximate method. So, it is better to call it approximate approximate determination of response. Okay. So, in this method, because in this case the forcing function is in the form of a narrow pulse, correct. So, then we would try to approximate this pulse as a impulse in the time domain, right. So, we studied in the lecture classes that what is Dirac delta function. So, Dirac delta function is an impulse acting at a certain point in time, right. So, it therefore here this narrow pulse we would like to approximate it as an ideal impulse, as a Dirac delta function. So, let us do that. So, let me again redraw the time domain forcing function here. So, this is the time domain function we are given f naught t naught, and what we are going to do is to approximate this as an impulsive function acting at the way at t is equal to 0, like this. Okay. So, let us call this, because it is like it's approximation. So, it is not, does not represent the exact force acting on the system. So, let us use a different symbol to represent this force. So, let me just put a prime over the f dash, right, as a function of time, correct. And now what is this f dash? This f dash is now we are going to write f dash is a function of time is equal to strength of the impulse produced by the actual force multiplied by the direct delta function del of t, right. So, what is I naught here? I naught is nothing but the strength of the impulse due to f of t. So, whatever is the actual force, we can find a value of impulse based on that, right. And how much is that? That is nothing but the integration of the area under the force time graph. In this case, this is essentially rectangular pulse. So, finding area is very straightforward. It is basically equal to f naught into t naught. But imagine if it was not rectangular, and let us say it is in the form of a half sine pulse like a speed breaker, right. So, there also we can determine the strength of impulse by integrating the area under the half sine pulse, that we can do, and that would be the impulse due to that force, right. So, therefore, this is I naught, and remember what is delta t? Delta t is a ideal impulse, right, which we have studied in the lecture classes. So, let us now so maybe for benefit of all, let me also draw here what is del of t. This is del of t, correct. It is a impulse concentrated at t is equal to 0, right, and it rises to infinite height in infinite simile small time, right. So, therefore, the f dash is basically multiplying this del by a scalar I naught, so that the impulse created by that function is equal to the impulse due to the actual force. So, that is the basis of equivalence. So, only approximation here is that now impulse we are assuming it is acting at a single instant of time at a time t is equal to 0 in a very infinite simile small time it is acting, but actual force is basically acting over a duration 0 to t naught. So, that is the approximation which is involved, right. So, after this approximation now there is no further approximation, this is the only approximation, correct. So, maybe I can write here that this is the approximation. So, this is the approximation. So, once we know we have approximated the force f of t by f dash t, now we can use the impulse response function to find the response, correct. So, I think maybe I can write here itself. So, therefore, now the response x, now also let me represent the x instead of by x, I will represent it by x dash, because it is the response found by using approximating the force by f dash t. So, it is not exactly the same as the true response or the exact response. So, x dash t, and this would be equal to the I naught multiplied by h of t, right, because the h of t is the response due to del of t. We already found this in the lecture classes that h of t is nothing but the response to del of t acting on the structure. And now if that is scaled by a scalar I naught, the impulse response would also get essentially scaled by scalar I naught, and that would produce the response. So, therefore, as x dash t will be then simply equal to I naught upon m omega d e to the power minus zeta omega n t into sine omega dt. So, that becomes the equation for the approximate response, right. And then we have been asked to find the amplitude. So, now we can work out the amplitude, we can go to next page now. So, let us determine the amplitude of the response, and amplitude is how much? If I call it, let us say, by A, then that is equal to I naught upon m omega d, because if you plot the curve for x dash, then it is going to be looking something like this, right. So, this curve would essentially look like this, and you have this going up, then something like this, right, this sign, and this is nothing but the amplitude, the maximum value of the response, right, that is the amplitude I naught. So, the remaining part is due to the time domain function sin e to the power minus zeta omega n t into sin omega dt, that is the time varying function, the coefficient of that, which is I naught upon m omega d, is the amplitude. So, now we can easily substitute the values here, where I naught, maybe one by one we can find out those values first and then substitute. So, therefore, now I naught is actually equal to f naught into T naught, and if I substitute these values, then I get 15 Newton second, right. Then other thing is omega n, which is under root k by m, and if I substitute the values of k and m, then I get 44.7 radians per second. Then I need to find damping factor, because I need to find the damped natural frequency. So, C upon Cc is equal to C upon 2 square root km, right, and if I substitute all these values here, I get 0.0559 as damping factor, and then I can find omega d. I can substitute omega n and zeta here, and I get the value as 44.65 radians per second, right, because damping factor is small. So, that is why omega n is only small, slightly smaller than omega n. Then I can now find A as 15 upon 2 into 44.65, and that gives me A is equal to 0.168 meters, correct. So, you can see in this manner we have found out the amplitude of the response, right. So, we have followed the approximate method, and then very easily we could find out the amplitude of the response. So, this could be an application, for example, a vehicle moving over a road and encounters a speed breaker, right. So, when it moves over a speed breaker, so similarly we can determine, of course one method could be exact method, where we describe the shape of the speed breaker as a displacement function, and then that displacement function acts on the base or the wheels of the vehicle, and they cause base excitation, and then we can model, for example, one simplest way could be to model it like a single degree of freedom system or a 2 degree of freedom system, and then determine the response of the body, that can be done. But then approximation method could, and then of course that requires performing convolution integral, right. But then the approximate method could be that following the way we did in this example, we approximate the excitation from the base in the form of impulses acting on the body of the car, right, which will come due to the impulse due to the suspension stiffness, and then due to suspension damping. Both these will give rise to some impulsive forces on the body of the car, and then we can easily work out approximately the excitation created or the response created on the body of the car when it is moving over the speed breaker, right. Okay, I think we can now go to the next example. Example number 2. Right. The receptance, maybe I can write here, quotient, the receptance FRF of a single degree of freedom system with viscous damping is given below. Find the mass and stiffness of the system using the concept of stiffness line and mass line. Respectively, right? And the FRF given here is like this. This is the frequency axis. This is around minus 80 and minus 100. Okay, and then we have something like minus 10. Yeah, then we have, this is the frequency in radians per second, right? And somewhere here is 10 raised to the power 0, then 10 raised to the power 1, 10 raised to the power 2, 10 raised to the power minus 1, and so on, right? So this is the receptance FRF that has been given, and let us proceed with the solution now. Okay. So we studied in the lecture classes the concept of stiffness line and mass line, isn't it? Which essentially we studied for single degree of freedom system, and we have shown that when the FRF plotted on a log frequency axis. So I think this also we should note that this essentially is the log frequency axis. It is the log axis, right? So that in the low frequency range, right, the single degree of freedom FRF with viscous damping, it is having a asymptote which is a horizontal line. So this stiffness line essentially is the asymptote to the FRF curve in the low frequency range, right, that we have studied, and it intersects the ordinate, right, it intersects the y axis at minus 20 log k, right. So we will make use of that to find the stiffness of the system. So let us mark now the stiffness line. So stiffness line is this. So this is the stiffness line, and this ordinate of the stiffness line is minus 20 log 10 k, right. So this is the, maybe I can write instead of here, let me write here, stiffness line, correct. And therefore stiffness line intersects the y axis at minus 20 log 10 k. So from the FRF plot, from the given FRF plot, we can read the FRF magnitude, right, at omega equal to at the place where this intersection occurs, correct. So, wherever it intersects the axis, right, y axis, that we can find out. So, essentially we are drawing a line tangent to the FRF curve, right, keeping it horizontal, right, and wherever it intersects the y axis is basically the value we have to read. So, from the graph this value turns out to be around 82 dB, correct. So, therefore, we say that the stiffness line intersects the y axis at minus 82 dB, correct, which means that minus 20 log 10 k is equal to minus 82, is not it. So, now easily we can determine this for, we can solve this for k, correct. So, from here the value of k comes around 1258 Newton per meter, correct. So, that is how we can find a value of the stiffness, right. So, the stiffness line okay. Now, let us use the mass line to determine the mass of the system. So, what is mass line? So, mass line has a slope of minus 40 dB per decade, right, has a slope of minus 40 dB per decade, correct, and it is an asymptote to the FRF curve in the high frequency range when omega is very large as compared to omega, correct, and is an asymptote to the FRF magnitude plot in the high frequency range. So, now how we are going to, so therefore, there are now two steps. First of all, we have to draw this mass line and then see that how that mass line can be used to find the mass, right. Let us first talk about the step number 1, how to plot the mass line. So, because the FRF this a mass line has a slope of minus 40 dB per decade, and because you can have several infinite number of lines with the same slope, right, all will be parallel to each other. So, our first therefore can step first way could be that we draw a line at minus 40 dB per decade, which is very easy because the FRF plot is given, and on the x axis the frequency is shown on the log scale. So, the frequency changes from, for example, 10 to the power 0 to 10 to the power 1, that is one decade, 10 to the power 1 to 10 to the power 2 is next decade, correct, because 10 to the power 1 is 10 radian per second, 10 to the power 2 is 100 radian per second. So, the ratio is 100 by 10 is 10. So, it means it increases by 1 decade on log axis. So, therefore, now on the y axis the change should be minus 40, it should drop, the value should drop by minus 40. So, in this way we can easily draw a line with a slope of minus 40 dB per decade. So, let me just draw that line. So, anywhere you can draw that line, the slope should be minus 40 dB per decade. Next thing what we should do is that we should then draw a line parallel to this line, right, such that that is asymptote to the FRF plot, correct, in the high frequency range. So, it means therefore, we will draw another line here, okay, which is going to be asymptote to the FRF plot in the high frequency range, you can see like this, and this line is now parallel to this line. So, this line is parallel to this line, which of course has a slope of, drawn at a slope of minus 40 dB per decade, right. And now we can just extend this line like this, right. So, this is nothing but the mass line. Okay. And then now next step is, once you have drawn the mass, this is the mass line, I think let me show the arrow properly, this is the mass line, right. And then how do you use this to find mass? As we studied in the lecture classes, we should find the intersection of this line with the ordinate at omega is equal to 1 radian per second. So, let us first draw the ordinate at omega equal to 1 radian per second, this is 1 radian per second. So, the ordinate is this, correct, this is the ordinate at omega equal to 1 radian per second, and we should look for the intersection of this. So, the intersection of this is this, right, and then we should see how much is the FRF magnitude at this point. So, this value we must see. So, this value is essentially equal to, it is equal to minus 20 log 10 m. So, this value is actually equal to minus 20 log 10 m, correct. So, if we read from the plot, we see that this value is, I think I need to little bit modify these graduations which I have shown here. This plot is not, the graduations are not properly scaled here, but this something like this could be around minus 5, then this is around minus 10, yeah, something like this. So, this value, it comes around minus 20 log 10 m, is turns around to be equal to around minus 14 dB, okay, around minus 14 dB. And if you solve this, you get m is equal to 5.01 kg, right. So, in this way you can see we can find the stiffness and mass of the system using the concept of stiffness line and mass line, okay. Maybe I can, we can go to the next example. Example 3. So, in this example and the next example, they are devoted to finding anti-resonance frequencies of a given system, right. And we are going to use and learn use of two different methods to find anti-resonance frequencies. In the first method, in this example, we are going to make use of the available model of the system, and in the next example, example 4, we would make use of the mass and stiffness matrix to find the anti-resonance frequencies, okay. So, let me write down the question first. Find anti-resonance frequencies for the FRF alpha 1 omega for the 2 degree of freedom system with the following model. So, omega n, this is given as 57.03 and maybe I think I can just rewrite this 5 and 114.78. So, these are the natural frequencies, the two natural frequencies, and the corresponding the mode shapes are these are mass normalized mode shapes. Okay, mass normalized mode shapes are given as 0.45, 0.15, 0.2 and minus 0.34, right. So, the model as we said in the lecture classes, it comprises of specification of natural frequency, mode shapes, right, and if damping is there, then the damping factor. In the present case, we are given an undamped model, right. So, here only the natural frequencies and mode shapes are given, right. So, let us proceed with the solution now. So, as we studied in the lecture classes, the anti-resonance frequencies for undamped FRFs or undamped system, they are the frequencies at which the FRF magnitude becomes 0, correct. And therefore, if you sketch this, let us say if I look at the FRF alpha 1 omega magnitude, if I plot this here, right, then this is going to look something like this. Something like this. So, you can see at this point what is happening, this is 0. So, this is nothing but the, if I call omega AR subscript for anti-resonance frequency. So, this is the frequency which is the anti-resonance frequency, and of course, the where it becomes very high, that is those are the resonant frequencies, and those frequencies already we have found out in our earlier session, right. We found the natural frequencies. Finding natural frequencies is basically finding resonance frequencies, which already we have done. So, by solving the eigenvalue problem, we have solved several examples. So, in this problem now we have to find what is this frequency, the anti-resonance frequency, where the FRF becomes 0, and based on the model now we are going to find this frequency. So, let us write down the expression for alpha 1. So, if you recall the expression for alpha 1, right, or maybe I can write down first the expression for the alpha jk, which is a very general expression, alpha jk omega. This for a 2 degree of freedom system will be equal to r is equal to 1 to 2 phi jr phi kr upon omega r square minus omega square. This is the expression, correct. And now if we write it for alpha 1, which means j is equal to, which means j is equal to 1 and k is equal to 1. If I use these two indices, then I can write this expression as r is equal to 1 to 2 phi, maybe I can write in expanded form directly, right. So, I can write this as phi 1, right, and then phi 1 upon omega 1 square minus omega square plus phi 1 2 because j and k are 1. So, the first index is always 1, the second index will be 1 in the first sum, 2 in the second sum. So, omega 2 square minus omega square. So, that becomes the expression for alpha 1, and if I take the LCM of this, then what it becomes? It becomes phi 1 square omega 2 square minus omega square plus phi 1 2 square omega 1 square minus omega square upon omega 1 square minus omega square omega 2 square minus omega square, correct. So, that becomes the expression for alpha 1. So, now we will invoke the basic definition of omega AR to find and proceed further, correct. And so, let us go to next page. So, at omega equal to omega r, we know that at omega is equal to omega a r, when the external frequency is equal to anti-resonance frequency, then at that frequency the magnitude is 0. So, we can say that the FRF is 0 at omega a r. Maybe I should write it like this, omega a r is equal to 0 at omega r. So, let us impose this condition on the previous equation. So, if you do that, then what happens? The left hand side would be then alpha 1 1 omega a r. Maybe I can substitute first the omega a r and then substitute the value of alpha 1 equal to 0, alpha 1 1 is 0, right. So, phi 1 1 square minus omega 2 square minus omega a r square plus phi 1 2 square omega 1 square minus omega a r square, correct, divided by omega 1 square minus omega a r square into omega 2 square minus omega a r square. So, this is the equation we get after substituting omega equal to omega, and now we know that at omega equal to omega r, alpha 1 1 omega a r is 0. So, left hand side will be 0. If left hand side is 0, then that can happen only when the numerator of the right hand side is 0, correct, because the denominator is non-zero at omega equal to omega r, right. So, even by cross multiplication that cancels out. So, therefore, we essentially can say that phi 1 1 square omega into omega 2 square minus omega a r square plus phi 1 2 square omega 1 square minus omega a r square is equal to 0, correct. So, if you now simplify this and we can solve then for omega a r, and that we can then write as phi 1 1 square omega 2 square minus plus phi 1 2 square omega 1 square divided by phi 1 1 square plus phi 1 2 square, correct. So, that becomes the a closed form expression for omega a r, right, and then we can substitute all the required quantities here. For example, then I can now say that phi 1 1 is actually equal to 0.45 square, omega 2 is 114.78 square, right, plus phi 1 2 is 0.2 square into 57.03 square divided by 0.45 square plus 0.2 square, right. So, if you compute this, we get omega a r is equal to 107.4 radians per second. So, that is nothing but the anti-resonance frequencies. So, this basically we did for 2 degree of freedom system, but if there is, let us say, n degree of freedom system, then what is going to happen? In the present case, for example, it is a 2 degree of freedom system. We got final equation which is in terms of omega square, right. It is a polynomial in omega a r square, right, and it is a linear polynomial, correct. But if you have an n degree of freedom system, then the expression you would get that would be basically a polynomial of degree n minus 1 in omega square, correct. So, let me write that here for an NDOF system NDF system. What is going to happen? So, essentially, if you look at this expression here, this expression, this is the expression for f for f, and it has ratio of two polynomials. There is one numerator polynomial, then we have denominator polynomial, right. So, if you look at this one, this is essentially the f for f, we can write in general as ratio of numerator polynomial and divided by denominator polynomial, right. So, for an n degree of freedom system, what is going to happen? The numerator polynomial, the roots of that essentially constitute the anti-resonance frequencies, right. Numerator polynomial roots are anti-resonant resonance frequencies, right, and it will be a polynomial of degree n minus 1 in omega square, correct. So, when you solve that polynomial, you will get n minus 1 resonant frequencies, anti-resonance frequencies, but again those all the roots may not actually be all real, correct. Some of them may be invalid, for example the complex values, right. So, therefore, those are to be discarded. Only the valid roots of these valid values of these n minus 1 roots, they constitute anti-resonance frequencies, right. So, which basically means that not all FRFs will have n minus 1 anti-resonance frequencies, only point FRFs will have n minus 1 anti-resonance frequencies. And in the present case, in the present example also we saw that the numerator polynomial is of degree 2 minus 1, because 2 is the degree of freedom. So, 2 minus 1 is 1. So, in the present case the degree of the polynomial, numerator polynomial is 1 in omega square, which led to one value of anti-resonance frequencies. So, I think maybe we can now go to the next example. So, let us take example number 4. So, find anti-resonance frequencies of anti-resonance frequencies in FRFs alpha 1 omega, alpha 2 omega and alpha 1 omega of a 2 degree of freedom system in mass and stiffness matrices given below. So, the mass matrix is 4 0 0 7 and the stiffness matrix is 20,000 minus 20,000 minus 20,000 and 80,000. Let us solve this problem. So, in this problem we have been given the mass and stiffness matrices of the system. So, we have been given a spatial model of the system. In the previous example, model was given, and from that we determined the entrance frequency. In this case, spatial model is given. So, basically we are finding omega AR, right, entrance frequencies from spatial model. So, this requires understanding of what we studied in the lecture classes, that how entrance frequencies can be found from the spatial model. For the benefit of all, I am just giving a quick summary of what is that theoretical background, right. Quick review of theoretical background, right. So, if you recall, we said that the alpha matrix, we know that the stiffness, the FRF matrix is inverse of the dynamic stiffness matrix, correct. So, what is this? Alpha is the FRF matrix of the system. For a 2 degree of freedom system, the FRF matrix will be 2 by 2, right. For a n degree, it is n by n. And then we have the Z matrix, which is the dynamic stiffness matrix, correct. And now, by definition of inverse, from the theory of matrix theory of matrices, we know that it is equal to the adjoint of matrix, that is Z, divided by the determinant of the matrix, determinant of Z, right. And what is adjoint of Z? We know that the adjoint of Z is nothing but the matrix of cofactors of Z divided by determinant of Z, right. So, this is for the FRF matrix. Now, let us now focus our attention on a particular FRF JK, right. So, if you are interested in particular FRF alpha JK, right, then let us use this expression to write that. So, alpha JK will be then equal to the JKth cofactor of Z, right. So, we have to look at the JKth cofactor of matrix Z. And what is the jkth cofactor? The jkth cofactor, as we know from the matrix algebra, is equal to -1 j plus k into determinant of Z j k divided by determinant of Z. Now, what is Z j k? What is Z j k? Z j k is the matrix obtained by deleting jth row and kth column of Z. So, if I have matrix Z, then I will delete the jth row and kth column and then compress the matrix. So, I get a new matrix of order 1 less than the parent matrix, right. So, that is nothing but ZJK, and determinant of that has to be taken to find the numerator. So, this is essentially the alpha JK, right. And now if I go to the next page now, then we can then say that the numerator, therefore, now for antithesis frequencies, at antithesis frequencies the FRF is 0, correct, at omega is equal to omega AR, alpha JK must be 0, that is by definition, correct. If that is so, then the numerator of the right hand side must be 0 of the expression we got, correct, and therefore determinant of ZJK has to be 0, because minus 1 to the power j plus k obviously cannot be 0, right. So, therefore, determinant of ZJK must be 0. So, therefore, determinant of ZJK should be equal to 0, right, and which means that, and what is now Z? It is the dynamic stiffness matrix, which is the k minus omega square m, that is the dynamic stiffness matrix. So, it means it is the KJK minus omega square m JK is equal to 0. So, that basically is the important expression we get, and remember here omega is nothing but is actually omega AR. So, it is not a bad idea then to is basically put subscript here AR, correct. So, determinant of KJK minus omega AR square into MJK must be equal to 0 at antithesis frequencies, correct. So, this also can be looked upon as a we can look upon we can think about an eigenvalue problem, right. The corresponding eigenvalue problem is KJK y to omega AR square m JK y. So, we can think about now a hypothetical system, right, whose natural frequencies are the antithesis frequencies. So, whatever this eigenvalue problem we have written, it essentially represents a hypothetical system whose stiffness and mass matrices are given by KJK and MJK, and solving the eigenvalue problem of that hypothetical system gives us the eigenvalues which actually are the natural frequencies, which are the antithesis frequencies of our original system. I mean for the FRF of that original system, not the system, because the antithesis frequencies do not belong to the system, they belong to a particular FRF, right, they are not global properties. So, that is why it is not correct to say that antithesis frequencies of the system, because antithesis frequencies they depend on the FRF, they basically belong to the FRF. FRF is of the system. So, therefore, now this is essentially the background theory. Let us use this theory now to find a FRF, the antithesis frequencies for the 3 FRFs we have been asked to find. So, let us first take the FRF alpha 1 omega AR of alpha 1 omega. So, we will make use of this equation, determinant equation, right. So, in this case j is equal to 1 and k is equal to 1. So, therefore, what is our governing equation then? The governing equation to find antithesis frequencies is k 1 minus omega AR square m 1 is equal to 0. This is the governing equation, and now we need to find what is k11 and m11. Maybe we can first find that and then substitute. So, let us first find k11. So, let me write here K matrix first, so that we can easily delete the required rows and columns. Right. So, now let us find K11. So, this is actually K, let me write that here, I think that is okay. So, let us, to find K11 we need to remove first row. So, let me strike off that row. So, this is the first row I am striking off, and then the first column. So, first column is this one, right. So, we have to remove these rows, and then the remaining matrix is the K11. So, it means that the remaining matrix then would be simply 80,000, right, like this. Similarly, let us determine M11. Now, M matrix was 4 0 0 7, correct. Let us strike the first column, first row, this is the first row gone and the first column gone. So, this gives me the M11, only 7 is left, correct. So, now in this way, now we can we have got K11 M11, and now we find a determinant. So, determinant of K11, that is, it is just a scalar 80,000 minus omega AR square M11 7 is equal to 0. So, essentially we get the expression that omega AR, right, is equal to 80,000 divided by 7 is equal to, so this gives me a value as 107 radians per second. So, in this way we get the entrance frequency for the FRF alpha 1. Let us now find the entrance frequencies for alpha 22, alpha 22. Omega AR of alpha 22. So, in this case now J is 2, K is 2, correct. So, our equation becomes determinant of K22 minus omega AR square M22 equal to 0, and let us determine. So, now we can easily see that from the matrix that K22, if we remove the second row and second column, correct, then let me write that here. You have 20,000 minus 20,000 minus 20,000 and 80,000, correct. Now, if I remove second row, which is this, and second column this, so I get 20,000, and then if I use if I determine M22, then I have 4007. So, now if I strike off second row and second column, then I get 4, correct, and therefore expression I would get would be determinant of 20,000 minus omega AR square into 4 is equal to 0. So, this essentially gives me omega AR is equal to 70.7 radians per second. So, these are all valid values you are getting. So, they represent two anti-resonance frequencies, correct. Let us now take the last FRF, that is omega AR of alpha 1 2. So, in this case J is equal to 1 and K is equal to 2, right, and therefore, the equation would be determinant of K 1 2 minus omega AR square M 1 2 equal to 0. and now if I determine the alpha k 1 2, then I have got 20,000 minus 20,000 minus 20,000 80,000, right. Now if I strike off the first row and second column, k is 2, like this. So then I am left with minus 20,000. Similarly, if I now determine M12, right, which is 4007, and if I now strike off the first row and second column, so then I get 0, correct. So in this manner, if I substitute these values here, what I essentially get is minus 20,000 minus omega AR square into 0 divided by this. So omega AR is equal to numerator minus 20,000 divided by 0 actually. So something like minus infinity kind of thing, right, minus infinity. So this is not a valid value, right. Maybe I will just go to next page to say a few more thing about this. So therefore this anti-resonance frequency omega AR we got minus infinity is not a valid value. If I show the FRF here for a alpha 1 2, I am showing here alpha 1 2 omega, right, then this FRF may be something like this, sorry. Something like this, okay. So this FRF actually does not have any anti-resonance frequencies. You can see between the two resonant frequencies, this is the first resonant frequency, this is second resonant frequency. Between these two there is no anti-resonance frequency. So as we studied in the lecture classes that the anti-resonance frequencies depend upon the the excitation coordinate and the response coordinate. So in a point FRF, just to recap that, if we have a point FRF like alpha JJ, so I am showing it for a system with n is equal to 3, for example, so you can have a point FRF, you will have this kind of FRF. So you have two anti-resonance frequencies, but if you if you look at a transfer FRF, so maybe this could be, let us say, alpha 1 1. If I look at a transfer FRF alpha 1 3, you may have one anti-resonance and you may not have other anti-resonance like this. So you have just one anti-resonance, correct. So therefore it depends on what is the excitation coordinate and response coordinate, and how far they are on the structure, how far they are located, that determines the occurrence of anti-resonance frequencies. Maybe now we can go to the next example. Example number 5. Question: a rotating machine is installed at degree of freedom 1 on a structure. The machine has rotating unbalance of 0.5 kg meter and runs at 600 rpm. Find displacement amplitude at degree of freedom 2 of the structure. The FRF between DOFs 1 and 2 obtained by measurement on the structure is given below. This FRF is alpha 1 2, right. This is the problem, and the FRF given, let us sketch that. So, this is the FRF and this is the frequency axis, this is in hertz, okay, and this is the receptance FRF alpha 1 2 in decibels, that is the y axis. So, this is also just to so the structure is like this. So, let us represent it by cantilever structure like this. And here the machine is mounted here such as a motor like this, and this is the degree of freedom 1, this is the DOF 1, right, and there is another degree of freedom of interest, this is DOF 2. So, at DOF 1 the machine is mounted, and at DOF 2 we need to find a response, and the frequency response function measured between DOF 1 and DOF 2 have been is given to us, and that is alpha 1 2, correct. And now we have to find what is the response at degree of freedom 2 due to unbalanced force at DOF 1. Let us proceed with the solution now. So, the point is that we can use our idea of the frequency response function. Frequency response function essentially gives you, for example, alpha 1 2, what does it say? It says that how much is the amplitude of the response at degree of freedom 1 if a unit amplitude harmonic excitation force of a certain frequency omega acts at degree of freedom 2. So, it gives us the amplitude of displacement response at degree of freedom 1 if a unit amplitude harmonic excitation force acts at degree of freedom 2. So, what will be our strategy to find the response at 1? Because we know what is the amplitude of the harmonic force acting at degree of freedom 1, that we can find from the information given in the problem, like unbalanced speed, we can determine that. And then you multiply the amplitude of the harmonic force with the FRF at the frequency of excitation, which is the rotation frequency of the machine. Then we can determine the amplitude of the response at degree of freedom. So, this is the strategy we are going to use. So, what we do is that first of all we measure, first we determine what is the excitation frequency, right. So, let us determine the excitation frequency first. Which is equal to which is 10 hertz actually as given in the problem, right, which actually because it is 600 rpm. So, that is essentially 600 divided by 60, right, 600 rpm divided by 60, that is 10 hertz. So, at 10 hertz we should read from the given FRF measurement what is the value of the FRF. So, we go to the graph and maybe roughly I can mark here, this is 10 hertz here and somewhere here and then here. So, this is around 80 dB, is around minus 80 dB, okay, this value. So, it means the FRF alpha 12 at 10 hertz is equal to minus 80 dB, correct. Next, now we can write our equation for displacement. What is the equation for displacement? We want to find the displacement amplitude degree of freedom 2. So, it means I want to know x2. So, I must know alpha 2 1 because the force is acting at degree of freedom 1 and response is required at degree of freedom 2. So, alpha 2 1 I must know, and then I must know what is the amplitude of the force at degree of freedom 1. So, this product will give me the x2, is not it. So, here we require alpha 2 1, but what has been given is alpha 1 2. So then what should we do? So, as we studied in the lectures that for a linear system, for a linear structure, the FRFs alpha 1 2 and alpha 2 1 are equal, right, because of the linearity. There is reciprocity relationship, right, for linear system, reciprocity principle is applicable. Alpha jk is equal to alpha kj, right, which basically means that the FRF matrix is symmetric. Which makes FRF matrix symmetric. So, which essentially means that in our case alpha 2 1 is actually equal to alpha 1 2, and therefore, I can make use of the graph given to actually find alpha 2 1. So, now let us determine what is F1, right. So, in our case the F1 is, let us determine that the force of excitation F1 amplitude is how much? It is m e omega square, correct, and m into e, the product is given as 0.5 multiplied by 2 pi 10 square, that comes around 1973.9 newtons, right, and therefore, now we can find x2. Now, we can find x2 by substituting f1 there. So, we get of course, we need to convert minus 80 dB into the linear value, because minus 80 dB is on the dB scale. So, let us I think first convert that. We can let us first convert minus 80 dB into linear value. So, minus 80 is equal to 20 log 10 alpha 2 1 upon 1. By default, the reference value to find dB is 1. So, now we can find alpha 2 1 from here. So, that alpha 2 1 value in dB, linear value will be 0.0001 meter per Newton. That is what we get. Okay. Okay. And now we substitute in the expression to find x2. So, that gives me 0.0001 into 1973.9 is equal to 0.1974 meter. So, that is the answer, right. So, in this way you can see we have found a amplitude of the displacement response at degree of freedom 2 due to excitation acting at degree of freedom 1. So, I think this also teaches us a very important strategy to find response for any practical structure due to some excitation acting on it. We do not always need the mathematical model for a given complex structure. Maybe mathematical model may not be known or is not available in the form of, let us say, finite model or stiffness and mass matrix. But this example, now we learn that if we have just the FRF between the 2 points of interest, just one FRF, right, at the where the machine is to be located and some point of interest where we want the response to be small. So, we can just go and and measure the FRF between those 2 points and use that to find the response at that point of interest due to any machine which is maybe planned to be installed at that on the structure, right, at certain point. So, without having access or availability of any detailed mathematical model, just a single measurement of FRF can be so much useful and may contain so much information. Okay. So, I think this is a very important practical tip to find responses through experimental measurements. So, I think in this way we come to the end of this session. We have solved 5 examples today based on the topics we studied in lectures 11 to 13, right. Now, I think we can stop here. Dhanyavad. Thank you.